Hi. So this is the second part of the counter design lecture, and we stopped at explaining what we are going to cover in this lecture. We said we will look into regular counters and irregular counters. We're going to look at the up counter, down counter, up and down counter, and um, for the most part for um, the regular counters, we're going to look at general design procedure and simplified design procedure. And then we will move to in the later on to the irregular counters. Just to remind ourselves of what is a regular counter, it is a counter if I have m flip-flops, okay, flip-flops, then a regular counter counts from 0 to 1, all the way to 2m minus 1. And then it repeats 0, 1, This is if it's an up count. If it is a down count, it will be 2m minus 1. Then it will decrease all the way to 0, and then the sequence repeat. Okay, this is the regular counter. Okay, all right. Okay, so let's talk about and discuss first the um, the design of um, the design of synchronous up counter. So we say that let's assume that we want to design this sequence 0, 1, 2, 3, then 0, 1, 2, and the sequence repeats. Well, obviously, you can see that the length of the sequence is 4. We learned that number of flip-flops equal log 2 of 4, and we take the ceiling, and that means we need 2 flip-flops. Okay? Assume that we will use the T flip-flops. T flip-flops. Okay? So, if we draw the state diagram, which is the very first step in the sequential design, because we are going to do the up counter, the general design process, and the simplified design procedure. So we'll start with the general design process of any sequential circuit, where we start with the state diagram. So the state diagram, we are in 0, 0. So what is these 0, 0? These are the 2 flip-flops, and we will assume that we have 2 flip-flops. Let's assume that they are 2 T flip-flops, and their name is Q1 and Q0. So the 0, 0 is Q1 and Q0. Okay, so this is 0, 0, Q1 and Q0. Whoops, let's see, didn't want to do that. Okay. Okay, so let's assume we are in state state 0, 0, which represent a count of 0. And then when a clock arrives, we go to a count of 0, 1, which represent 1 in counting. Then when I receive a clock, we will go to 1, 0, which represents 2. And then when there is a clock comes in, we go to a count 1, 1, which represents 3. And then we go back to 0. So this is exactly we're doing this sequence. We are doing this sequence. Okay, so again, these two digits or these two bits are Q1 and Q0, the values of Q1 and Q0. Next, what I do in the design process is that I construct my what? My state table. So I say present state, next state, okay? And then I'll use T1 and T0 because these are the inputs that I'm trying to find out. Okay, present state Q1, Q0, next state of Q1, T plus 1, and Q0 t plus 1. Okay, and these are the inputs. Okay, so let's do those now. Okay, so let's choose different color here. If I am in state 0 0, the next state will be 0 1. If I'm in state 0 1, the next state will be 1 0. If I'm in state 1 0, the next state will be 1 1. If I'm in state 1 1, the next state will be 0 0. I am just plugging in the state diagram in my state table. Now we learned that we do this. Next, will use the excitation table to compute the values of T1 and T0. How to compute the values? Well, the excitation table of a T flip-flop is simply says if the present state and the next state are the same, like this case. Okay, let's choose different color here. Like this case here, they are the same, then T will be, all right, so Q1 present state is 0, Q1 next state is 0, then T1 will be 0. Now, let's take a look here. Q1 present state is 0, Q1 next state is 1, then T is 1 because present state and next state are different. Okay, Q1 present state is 1, Q1 next state is 1. They are the same, so the input will be 0. Q1 present state is 1, Q1 next state is 0, so it is 1. Okay, now let's take a look at Q0, which impacts the input T0. So 0, 1, 1, they are different. 1, 0, different. The present and next state are different. 0, 1, different. 1, 1, 0, different. Okay, so let's now write the equations for T1 and T0. T0, it's 1, very clear. How about T1? T1, it looks like an XOR to me, okay? It's an XOR. We are basically, let's see, no, it's not an XOR, it's basically a Q0, sorry. This is a Q0, T1 is a Q0, okay? Now, so because you can see here, so 0, 0, 1, 1, 0, 0, 1, 1. So T1 is Q0. We can use the K-maps and alls to verify our solution, but anyway. So let's now, the final step is to draw the circuit. So let's draw the circuit. So we'll draw the circuit. Okay, so the very first flop here is T, Q, this is T0, Q0, and this is the clock here. And then the second flip-flop here is TQ, okay, and this is my clock here. Okay, notice they are connected because it says the two flops are connected to the same clock because it's a synchronous design. And this is T1 and this is Q1. Okay, now let's see what are the inputs here. Okay, so the inputs for the T0 is 1, okay, and the input for T1 is Q0, okay, and here is my Q1. So this is my counter, okay. We can see how very simple. T flip-flops, by the way, facilitates counter. D flip-flops somehow makes counters a little more involved. So let's try D flip-flop might as well. Okay, so let's assume that we are using D flip-flops. Let's assume that we are using D flip-flops. D flip-flops. Okay, so the same design process doesn't change. Present state, next state, state diagram, except that now instead of T1 and T0, we'll have D1 and D0. Recall in the design of sequential circuit that the D flip-flop has very special and super property, which says that the next state is the same as the D's. So I just copy the next state, 0, 1, 1, 0, and 1, 0, 1, 0. Okay, so the next state is exactly like the D's are the same as the next state. Now, so we can simplify this to be, so do D0 equals, it's exactly the opposite of Q0 prime, and D1 equals the exclusive OR of Q0 and Q1. Okay, all right, now, so let's draw the flip-flops right now. So here are, let's draw the flip-flops. Let's just choose a different color here. Let's choose a blue, okay? So here's my two flip-flops. The first flip-flop, okay? This is D, this is Q, Q0, and Q0 prime, okay? And this is my D1, okay? Now, and and let's draw the second one. So this is the second D flip-flop, D and Q. So this is D1, this is D1, and this is Q1. Okay. Now, so um, for let's try a different color for connectivity. Okay, so let's connect D0 equals Q0 prime. So this is Q0 prime, goes all the way as an input to D0. So this is D0, by the way, not D1. Okay, let's clarify this. We'll take an eraser here and say this is not okay. And now let's go take a pen here and make sure that this is, we clearly indicate that this is D0. Okay, all right. Now, and how about D1? D1 is the exclusive OR. Okay, so it's an exclusive OR function. It's an exclusive OR function. So we will have this Q0 and Q1 comes in all the way here. We create an exclusive OR gate and we connect it to D1. Then we should indicate the clock. Okay, here's the clock because these are flip-flops. Here's one clock, there's another clock. The triangle represents a clock. Okay, and here is, and this is the clock. Okay, so this is a synchronized up counter using T flip-flops and D flip-flops. Clearly, T flip-flops makes the design easier. The D flip-flops somehow complicates slightly the design. T flip-flops are more appropriate for counter design than D flip-flops. Okay, so this is the up count. Well, we talked about the up count counter in terms of the general design process. We say that we will explain the general and then the simplified. Let's talk about the simplified process. Okay, so the simplified says the following. Okay, so the simplified says that suppose I have 3 flip-flops and I'm doing the count for these flip-flops from, let's say, 0 0 all the way to 1 1 1 1. Okay, so 0 0 1, this is 2, this is 3, 4, 5, 6, and 7. Okay, and clearly here I have this is Q1, Q2, Q1, and Q0. Okay, now the simplified method says the simplified typically uses T flip-flop or JK flip-flop where we short the J and K, because a T flip-flop is equivalent to JK flip-flop, okay, when you short the J and the K. They are the same. A T flip-flop is the same as JK flip-flop provided you short the J and the K input. Okay, so let's take a look here. So notice here that the 0 and 1, the Q0 always changes, always changes. Every count, the Q0 changes. So, which says that if I am building a counter using T flip-flops, so this is T, this is Q, okay, and this is T0, I can use I can use a 1 here for this Q0. So Q0 basically uses a 1. So every time, every clock Q0 flips. If it is a 1, next state becomes a 0. If it's a current state is a 0, next state becomes a 1, and so on and so forth. Because you can see that it's always toggling. Okay, so this is the first observation. Let's take a look at the second observation. So the second observation for Q1 is that look at here, 000 1111 00111, and then it flips the other side when we go to the next 00. It turned out we do this flipping whenever Q0 is 1. Notice here, whenever Q0 is 1, we do this flipping. Uh-huh. So that's a hint for us, which means when I draw my counter here, which is for Q1, okay, so this is my T input, and this is my T1, and this is my Q, and this is my Q1, okay? What happened is that all what I need to do here is that I can connect Q0 right away to the T flip-flop, because whenever Q0 becomes a 1, we flip the Q1, as we have seen here in my observation. Okay, so how about Q2? Okay, well, let's take a look at Q2. What about it? So Q2, let's see here. So this is Q2, 00000, then 111111, and then the 1111 goes and changes to 00. Notice that the change from 00 here happens right here, and this is when both Q0 and Q1 are 1s. Similarly at the bottom here, meaning that for flip-flop, third flip-flop, with the output of, so this is QT, this is Q2, and this is T2, what happened is that I need to make sure, okay, let's just use a different color here. I want to make sure that both Q0 and Q1 are 1s, and if they are 1s, I go and toggle Q3. In fact, we can continue with this design procedure, and this is the basis of counters, up counters, and we can continue adding flip-flops. In fact, at flip-flops at Qn, okay, Qn, okay, which has an input of Tn. It has an input AND gate which ANDs Q0 all the way to Qn minus 1. This will toggle this T flip-flop for Qn. Now, so this is the general simplified form. So now, don't forget always the clock. It's very important we don't forget it, because this is digital design. So this is my clock. Okay, so this is the simplified method for an synchronized up counter. Okay, all right. Okay, so now let's now discuss uh, the um, the synchronous design. Synchronous, oops, sorry. Synchronous design of down counter. Okay, counter. Okay, so assume that we are trying to do the design of the following counting sequence: 7, 6, 5, 4, 3, 2, 1, 0, and then go back. Okay. So obviously, I can count these sequence. It very clearly, it is obvious that I need how many flip-flops? 3 flip-flops. So I need Q2, Q1, Q0, and now I need to count from 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, and then go back here. So if I draw the state diagram, okay, the state diagram, I'll start from, oops, sorry, okay, I'll start from, let's say, state 1, 1, 1, 1, 1, 1. After 1 clock, I go to state, so this is 7. I go to state which represents count 6, and then 1 decrement by 1, state which represent 5, 1, 0, 1. I decrement by 1, go to state which represents 4, 1, 0, 0, and then count, go to a state which represents 3, and count, go to a state which represents 2, 0, 1, 0, and count, go to a state which represents um, 0, 0, 1, then count down, go to a state which represents 0, 0, 0, and then one more count and go back to 1, 1, 1. So this is the state diagram. Okay, and then I can I can go to the same process, continue. We have present state, next state, okay, and the inputs of the flip-flops. Okay, so present state, I construct the state table, okay, and continue the design process much like the similar to the previous example. We get the inputs equations and then we draw the counter. Okay, since it's very similar to the up counter, I'm going to leave it at this point. And then, so this is what I described is the general design, okay, procedure. Let's go for the simplified. We like the simplified. Okay, so let's look at the simplified. So the simplified design procedure, we need let's take a look at the observation where we said that we were at 1, 1, 1, then we went 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0. So this is obviously here is Q2, Q1, and Q0. Okay, similar to up count, it is very clear that Q0 always invert. Okay, which means if I draw a T flip-flop, okay, so this is T flip-flop, this input will be 1. This is for, whoops, so this is always invert. Okay, so this is the very first T flip-flop. Q, so this is T1, T0, this is Q0. Okay, this is Q0 prime. Okay, so the very first input here will be a 1 for this because it always inverts. Now let's take a look at Q1. So you can see Q1 1, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0. So when does the switch happen? When Q0 is 0. When Q0 is 0, the switch happens. So Q1 flips whenever Q0 is 0. So that's easy. So what we do here, we draw the Q1. So here is my Q1. Okay, so this is my Q1, and this is Q1 prime. This is my T, and this is my T1. Okay, so what do I do? I connect Okay, I connect this here, right here to I connect Q0 because whenever Q0 is 0, Q0 prime will be 1 and it will toggle the flip-flop of Q1. Now, let's take a look at Q2. Okay, so let's take a look at Q2. Notice Q2, 0, 0, 0, all the way 1 here, 0, 0, 0, and then flips. When does it flip? Ah, you can see that when Q0 and Q1 are zeros. So, okay, so let's go and say, okay, so here is my last flip-flop. Here is the T. This is my Q2. It's my Q2 prime. Okay, this is my T2. Okay, so I take this Q0 here, Q0 prime, and Q1 prime. They get into an AND gate. Okay, and then send it to T0. Okay, all right. Then don't forget the clock. Okay, so here's my clock because these are flip-flops and we are talking about synchronized design. I should always show my clock. Okay, in general, if we keep continuing, you will see that QN, notice we stopped at Q2. QN, whatever the N is, has a TN input where this TN has an AND gate of Q0 all the way to Q0 prime, sorry, all the way to Qn minus 1 prime. Okay. Another also observation, you should always uh, uh, recognize that the T flip-flop is equivalent to JK flip-flop with shorted inputs. So this is the J, this is the K, this is the Q. These are the same. These are the same. So I can take this one and plug it in this drawing and it will work just fine. Okay. All right. Okay, so this is the simplified method for down counter. Okay, so the last circuit we will discuss here in this lecture is the up and down counter. The up and down counter. So the up and down counter. So we'll talk about synchronous up and down count. Since I have up count and down count, I need a control signal. I'll call it X. And if X equals 0, then I'm going to count up. If X equals 1, then I'm going to count down. Okay, so let's try this state diagram. So I'm going to assume that I will like to count 0, 1, 2, 3, then 0, etc. Or 3, 2, 1, 0, 3, etc. So this is my up and this is my down. I have to be able to do both. So since the sequence is the length of the sequence is 4 codes of binary, so I need only 2 flip-flops. Okay. So now let's draw the state diagram. So the state diagram is that if I am in state 0, 0 and X is 0, then I'm going to increment to 0, 1. Right? If X is 0, right, I'm going to go to 1, 0. If X is 0, I'm going to go to 1, 1. And if X is 0, I'm going to go to 0, 0. Now, what happened if X is 1? Well, if X is 1, then I will decrement 3 to 2. And if X is 1, I will decrement state 2 to 1. 0, 1, 0, 2, 0, 1. And if I'm in state 0, 1, I have an X equals 1, right? Then I will go to 0, 0. If I am in state 0, 0 and I decrement, I'll go to an X is 1, X is 1 here. I'll go to state 1, 1. Okay. Now, what do? I'll construct the state table, much like any design process that we have, sequence and design, that we have been doing so far. Okay, so I have here. Let's do this. Okay, so 1, 2, 3, 4. Okay, okay, just constructing my table here. Okay, so now what's my present state? Present state. It will be Q1 and Q0. I'm gonna assume that of course I know by now that I need two flip-flops. Let's assume that we are using JK flip-flops for just a change. Okay, and my input is X. Okay, so this is my input, and next state is what? Is Q1, Q0, and then I have to find out the input of J1, K1, J0, and K0. Okay, now, so let's see, take these inputs. I'm 0, 0. So if I'm in state 0, 0, which is this one here, oops, sorry. Do it in different color. Okay, so if I'm in state 0, 0, which is this one here, if I have input 0, I'll go to a state 0, 1. If I have an input of a 1, right, I'll go to a state of 0, 0, a 1. I'll go to a state of 1, 1, 1, 1. Okay? Find state 0, 1, 0, 1. And my input is 0. I go to this state 1, 0, 1. So 0, input of a 0, I'll go to 1, 0. Well, if I have an input of a 1, okay, so which is this one here, I'll go to a state 0, 0. So 0, 1, 1, I'll go to a state 0, 0. If I'm in a state 1, 0, which is this one here, and I have, oops, sorry, that was not intended. Okay, and if I'm in state 1, 0, and I have an input of a 0, okay, let's check on the battery. No, battery is good. Okay, and oops. So if I'm state 1, 0, and there is an input of a 0, so I'll go to state 1, 1, 1, 1. If I'm in state 1, 0, 1, 0, okay, it's just um, okay, I'll go back here and okay, so this is 1, 0, and I have a 1, so 1, 0, I have a 1, I go to 0, 1. If I'm in state 1, 1, okay, which is this one here, I get an input of a 0, go to 0, 0. And if I have an input of one, a present state of 1, 1, and I have an x of 1, okay, I'll go back to 1, 0. Okay, 1, 0. Okay, now I need the inputs. So I have present state, I have state next state. I need the input for JK. So what do I have? I have to use the the excitation table, QT, QT plus 1. Okay, and it gives me J and K. So this is 0, 0, 0, 1, 1, 0, 1, 1. So this will be 0, x, 1, x. Okay, so this is x here. And this is x1, x0. So now I can see, now let's use a different color here, red for example. So I can see the present state here of Q1 is 0, next state is 0. So this will be what? 0x, 0x, okay? And the present state of Q1, okay, is what? 0. Next state is 1, okay? So 0, 1, 0, 1, it's 1x on the J and K input for Q1. And okay, similarly 0, 1, 1x, okay, and 0, 0, 0x, right? And here present state 1, 1, 1, 1, which is this one here, right here. This is x0, and 1 and 0, okay, and 1 and 0, x1, x0, x1, okay, and then the other next one is similar, and this will be x0 as well. You can do the same thing, okay? So for Q0, present state is 0, next state is 1, 0, 1 is 1x, 1x, okay? Similar the next one, 1x, okay? And here present state is 1, next state is 0, 1, 0 here, x1, x1, similar x1, okay, and this is, we are almost copying the next 4 as the previous 4 as well, okay? So x1, x1, the inputs are similar, the patterns are similar, so I'm doing, for saving of time, I'm doing it quickly here. Okay, clearly we can see here that j, so let's do this. Okay, so you see k0, whoa, 1k j0, wow, that's nice, that's nice. So k0 looks like it is minimized to 1, j0 as well to 1. How about k1 and j1? If we work out the k-map for them, j1 can be minimized as q0 XOR x, and k1 can be minimized at q0 XOR x. Oops, XOR x. Okay. Okay. So let's draw the circuit now. Okay. So flip-flops. First flip-flop. This is the first flip-flop. J, K, Q. This is J0. This is K0. This is Q0. Okay. And then the second flip-flop. J, K, and Q. This is J2, and this is K2. Okay. Now, what we know is that J0 and K0, both of them equal 1, and J2 and equal, we have to XOR the Q0 with X, and then short these guys together, connect them to the output of the XOR gate. Okay. Left one more item here. As always, don't forget the clock. This is a synchronous system and a flip-flop, so we connect them to a single clock as shown here. Okay, so this is an synchronous up down counter. This is the general design process. Unfortunately, there is no simplified method for the up down counter. We stop at this point and we'll continue the rest of counters in the next part of this lecture. Thank you very much.